Hi there, we're the team kitmetrics and friends, and we're going to present our results for the HIDER International Virtual COVID Data Challenge. And in this challenge, we were dealing with two tasks. The first task was to impute missing data of clinical assessments, and secondly was to classify disease severity. And here the focus was especially on using CT scans and X-rays. However, we also realized quite early in for the second task that not all patients have image data provided. So we knew that the first task, the imputing of missing data of the clinical assessments, was also really important to find a good solution. To tackle the first task, the clinical data imputation, of course, we had the challenge that a lot of data points were missing. And especially a lot of data points were missing in the training set as well. And thus, we also had then an issue to really figure out how to evaluate the quality of the imputation. We found a couple of solutions and tried many different approaches, like similarity-based methods and training autoencoders, using k-nearest neighbors imputers, iterative imputations, and tried grouping different parameter groupings there. But however, by evaluating our methods and using generating more missing values in a cross-validation term, and then evaluating our results on those missing values, we found that the best method was simple k-nearest neighbors clustering with 20 neighbors. And we see the imputation error here on the artificially generated missing values on the right side. So then we came to the second task to predict disease severity. Here our challenges were that we had only few images in the training data, that the quality of we were unsure about the quality of the image data, and also because image data was missing for certain patients, we were wondering how to best combine the different data sources, so to combine clinical data and X-rays. Yes. And again, we came to use several approaches. So we used convolutional neural networks to directly classify disease severity, whether it's a mild or a severe case. We used clinical data directly using common approaches such as random forest, support vector machines, or rich classifiers. Or we used features generated from pre-trained convolutional neural networks, and also then used random forest, support vector machines, and rich classifiers on those newly generated features. And finally, we then decided to use an ensemble of those different methods. The results of our training showed that logistic regression with 76% accuracy was by far the best model. However, random forest and rich regressions came in second. We also found that using data derived from the images didn't have such a great accuracy. And so then we used, in the end, a weighted ensemble of the best models, which we predicted submitted to the challenge. So in conclusion, we found that we had this was a quite short time frame to deal with lots of unfamiliar data, and especially a lot of missing data in the data set. And then also we found it hard to incorporate information from the different sources. And then especially for imaging data, we had little data to train really a new neural network approach, and also even little data for fine-tuning. But in the end, we also could show that more simple machine learning methods outperformed the more complex neural networks, and focusing on imputation was, at least in our sense, the best way to predict the disease severity on the test set. And yes, and here we are again as our team, consisting of Martin, Konstantin, Niels, Arne, Daniel, and me, Simon, and thank you for listening.